Okay, here we are. Whoa, look at that background. That's fabulous.
Right.
That's Don Thomas next to me. He's a volcanologist with based mostly in Hilo, but he happens to be here in Honolulu today. Otherwise, we would have caught up by Skype, you know.
Right.
And we're calling this show Sustainable Hawaii. That's our series, Sustainable Hawaii. And it's I've named it, Don, a hot time in the old town of Pahoa tonight.
That's an appropriate title.
So let's talk about being a volcanologist. First of all, I want to be clear. Everybody should understand that nothing to do with Star Trek or Dr. Spock. Okay.
Correct.
That said, what is it?
What is it? It really is a very broad field. We study volcanoes, volcanic processes. Ultimately, our goal is to understand sort of how volcanoes operate, how the plumbing system interacts both in the shallow environment and at depth. And sort of one of the major focuses of the work is to really be able to mitigate the volcano hazards and sort of understand when a volcano is going to erupt, sort of the magnitude of the eruptions, and really try to manage the volcano hazards and understand sort of how the volcanic systems operate is really the bottom line.
Yeah, I mean, that puts it in a simplistic way, but there's much more. So what do you have to study in order to become a volcanologist?
Well, as I say,
Don't say volcanology.
Right. Well, no. It is an earth science, but it really is interdisciplinary, where we're looking at the geologic side of things, where we're looking at mineralogy, we're looking at the chemistry of the lavas, we're looking at geophysics and the physics of a volcanic system. And as the field is pursued today, you know, it is very broad. Our technologies have gone from being exclusively field observations to progressively more remote sensing and even satellite observations. And so all of the fields that are involved, physics, chemistry, very high-level math, as well as just simple geology.
We had a show a few weeks ago about drones.
Yes.
You know, unmanned something vehicles,
Mm-hmm.
Unmanned or autonomous, whatever.
Yeah. Yeah.
And they talked about the use of drones to identify exactly what lava was doing. So is that a new entry? Is it of consequence in the scientific world?
I think so. I think having access to drones will significantly alter how we do some of our work. It will help us gather better data. Of course, you know, one of the issues that all of us in the field that are doing field work have to be aware of are the hazards. And you know, things that we can do remotely, including doing field observations, very detailed measurements, so-called LiDAR, mapping the ground surface, sampling the gases, making these observations remotely is actually a good deal safer than being out there in the field itself.
How do you deploy these instruments? You come down over the field with a helicopter and drop them there because they're essentially disposable.
Well, with the drones, they're working right now on essentially, again, the autonomous vehicles that would have sampling instrumentation, or we do a lot of work spectroscopically, where we're able to either directly using infrared sensing, we can do a chemical analysis of the gases immediately after the gases are emitted. There's a new instrument that is still in the research phase that can actually do a much broader analysis. We haven't yet deployed that in the field, but that's something that we want to do.
So you've been doing this for a while. I mean, where'd you take your training?
Well, actually, my training was at the University of Hawaii. I came to the University of Hawaii in 1972, and my field, sort of primary field at the time, was chemistry. I was interested in gas chemistry, and my dissertation research was studying the fumarole gases discharged by Kilauea Our objective in that effort was actually to look at the chemistry of the gases and see if there were reproducible changes that occurred prior to eruptions, and it was all in the interest of being able to forecast eruptive activity. And of course, with Kilauea, the forecasting the activity is not as critically important as it is in, say, a volcano like Pinatubo, where we have a volcano that's been quiescent for decades to centuries, and we see unrest, we see the volcano seem to reawaken, and we really have to know with sufficient advance warning whether that reawakening is going to lead to a major eruption in order to evacuate residents in the vicinity. And actually, Pinatubo was one of the earliest volcanoes. This was the volcano in the Philippines that we actually did have an accurate forecast. It was based on monitoring the seismic activity, changes in the shape of the volcano. It's the field is called geodesy.
Geodesy. What a wonderful word.
we make measurements of inflation of the volcano and use that to infer the size of the magma body that is ascending up into the interior of the volcano. We also monitor the gas discharge. And the combination of those techniques, as well as actually the field mapping, this is something that a lot of folks don't understand. We look at the history of the volcano as well to understand the type of eruption that's typical for that volcano. So it's the entire suite of techniques that we have to apply. And in that case, the U.S. Geological Survey was very heavily involved in the monitoring and the effort for Pinatubo. And they accurately forecast that there was an eruption imminent, and they were able to evacuate on the order of 200,000 people in the surrounding communities prior to that eruption.
This is a very important case study, and if you don't mind, I'd like to divert a little bit and talk about it. One thing that comes to me, anyway, just listening to you, is that it's kind of like a blister. That, if it's relieved in some way, like the volcanoes in Hawaii, then the pressure under the mantle of the Earth, and I don't know if that's the right term,
that deep,
the crust of the Earth won't build up so much because it's being relieved. But if you find that it's not being relieved, dormant, as in the case of Pinatubo, for decades, then you know that the pressure is down there and there's nowhere for it to go, and therefore it's more dangerous. Am I right?
Well, not completely.
Seems like a good theory anyway.
Good, nice try. No, different volcanoes. Hawaii is fortunate in that the magma that is supplying Kilauea has a relatively low viscosity, and it is able to rise fairly easily to the surface. Gases are able to come out of solution. This is something, again, most people don't understand, is that magma contains large quantities of water vapor, sulfur dioxide, carbon dioxide, that as it approaches the surface, that gas wants to come out of that magma. If it can come out easily, as in the case of Kilauea, then the eruptions are not as likely to become explosive. In a volcano like Pinatubo, the magmas there are much more viscous. The chemistry is different. Again, bring in the chemistry. Mm-hmm. And as that magma came to the surface, there was very serious concern that its past history was that when it erupted violently, and that's exactly what happened.
So in the Pinatubo case study, if you will, the community of volcanologists found a way to predict accurately. We should talk about what accuracy means in this context. Predict, when it was going to happen, and therefore save a lot of lives. It's a study that sounds to me like really important going forward. Important not only for the volcanologists on an academic level, but for the community and for the world.
Absolutely.
So, query: what tools, what analysis, what kind of data and data analysis were used in order to make that prediction?
Actually the oldest method that is still, and one of the most valuable methods is seismology. We study the seismic activity, monitor the seismic activity within the volcano, and we analyze the seismic activity for where it's occurring, how deep that seismic activity is occurring, are the rates increasing or decreasing, what types of seismic events, and there are multiple types of seismic events that can be associated with magma movement, with increases in inflation of the volcano. And so that is a technology that's been with us at varying levels of sophistication from the early part of the 20th century.
Inflation.
Inflation
would be the ground
comes up. The volcano will inflate. The volcano, in a sense, is almost like a balloon, or it has a balloon inside the magma reservoir. That magma will rise up into that reservoir, and the structure of the mountain will have to accommodate that new mass that's being injected into the base of the volcano.
So it's rock, it's stone, it's heavy, it doesn't move so easily.
Right.
How can you tell that it moved, that it inflated?
Well, back to seismology. The seismology, when that rock is, and the rock, as you say, is very dense, it's very stiff, the only way you get it to move is to break it. And when that rock is broken, we see that seismic activity. But we also see changes in the ground level, and that's the geodetic monitoring methods. And we've been able to use that since the Roman times.
Geodetic?
Geodetic meaning geodesy, the measurement of the ground level. And
like altitude?
Like altitude, exactly. We have, there are monitoring instruments at the summit of Kilauea and the summit of Mauna Loa that look for changes in elevation, in changes of the tilt of the flank of the volcano. And those measurements can tell us, we have models now that will estimate the volume of magma that's been intruded inside the volcano and can track how that volume increases or decreases. And of course, the other major method that really has revolutionized the field is global positioning. We have recording GPS instruments that the U.S. Geological Survey and the university have deployed over the summit areas of Kilauea and Mauna Loa, and they're continuously recording, and they're being monitored on an ongoing basis, and we can tell when magma is being intruded into Mauna Loa.
So are they sending it back by radio, or do you have to go out?
Yes, it's radio telemetry back to the volcano observatory, and they track those changes on an ongoing basis. Several years ago, Mauna Loa has been undergoing, or had been undergoing, a very long period of actually deflation, of very slight shrinking after the 1984 eruption. But in about, I believe it was 2002 or 2004, they noticed that deflationary episode had ended and had actually started to increase. There was an increase in inflation, which suggested that there was magma perhaps moving up into Mauna Loa's magma reservoir.
What does deflation signify?
Well, deflation probably is associated with cooling of the intruded magma. Essentially, when you have an eruption, not all of the magma that comes up into the volcano is erupted, is extruded. Some of it is placed underground, and over time it loses its heat, and there's a slight contraction as that process goes on. That's
Don Thomas with Hilo, I guess UH in general.
UH in general.
It's part of SOEST, no?
Yes, my affiliation is with the Hawaii Institute of Geophysics and Planetology, which is within SOEST.
And he's a volcanologist for a long time, back from the 70s, I guess. And we're talking on sustainable Hawaii, and we call the show A Hot Time in the Old Town of Pahoa. We'll be right back.
Hi, I'm Ethan Allen. I'm the host of Likeable Science on ThinkTech Hawaii. We talk about why people should like science, why science is actually fun, how science is a dynamic and vital part of everyone's life, why everyone, every man, woman, and child on the planet should really know science, should love science, should be familiar with science. So it's a great show. People come on here and have interesting conversations with us. They tell us why they do what they do, why they love it, why we should love it too. I hope you'll join us every Friday, 1 to 2 p.m. And of course, you can see it anytime on YouTube. Aloha.
Okay, we're back. We're live. I'm Jay Fidell here on ThinkTech's Sustainable Hawaii. We're talking about a hot time in the old town of Pahoa on the Big Island tonight with Don Thomas, a volcanologist with UH and the Institute for Geophysics and Planetology, yeah, which is right there as you make the left turn, just next to the engineering school, right
exactly.
near the East-West Center, where I think God lives there or something. We've had a lot of guests from SOWEST.
Really?
A lot of guests, regular basis. Anyway, so Don, you're talking about you know, the measurements, the inflation, the deflation, you know, the sort of the characteristics of the mountain, so to speak.
Right.
But how does that take you to an A or a nay? To you better, you know, vacate or not vacate?
Well, again, we're looking at a multitude of different factors, and included as well with seismology and measuring deformation is another term for the geodetic measurements. We look at the gas geochemistry, and what we do is try to integrate all of these methods together. We look at the seismology, we can tell whether magma is moving underground or not, and we can begin to identify how shallow that magma is. With the geodetic surveys, we've developed models, numerical models. If you have so much inflation over this region, then we can make an estimate of the volume of magma that has caused that change in the shape of the volcano. We look at the gas geochemistry. That tells us, in a sense, the overall heat flow, the amount of energy that's moving up into that system, and how open that system is. And the analogy that I use when I'm talking about this with students is that it's sort of the four blind men and the elephant, where, you know, each individual technique will give you a piece of the whole picture. And when you put those pieces together, then you can make an informed estimate of the likelihood of a significant eruption. And let me backtrack a little bit, because the historical geology, the mapping is also a critical element.
When you say mapping, you mean the topological mapping of what
Exactly.
does the surface of the Earth look like, because you need that to apply this other data and see how it interacts, yeah?
That's true, as well that what we do is we're mapping the deposits.
Underneath.
Well, sort of where they're exposed at the surface. And if you, as they did at Pinatubo, they went out into the stream-cut valleys and mapped these layers of ash that were 20, 30, 40 meters thick, then that says, okay, when this volcano erupts, it erupts in a big way.
That's old ash or new ash?
That's old ash.
Old ash.
That's ash from the last eruption or the last 5 eruptions. And that the mapping is intended to try to sort that out. Okay, when did this event occur? How big was it? How far back into the history? How many times has this type of eruption occurred? And that information together then goes into an analysis of the likelihood of a major eruption or a minor eruption.
Can I just jump
Sure.
back for a minute? So history is part of this.
Absolutely.
You know, I mean, I think people may have sort of a grade school, as I do, impression of all of this, and they see the world as a kind of crusty thing, and then inside is all this liquid magma stuff, which moves around, swirling and bubbling, and you know, bubble, toil and trouble, just out of Shakespeare. But in fact, I think I'm right on this. It doesn't move that much.
No.
It's hot and it's got gas, but it
right.
doesn't move much.
Right.
Which means that when you can find out what happened in the last eruption, whatever your means, that history will help you predict on the next one.
Right. It gives you a sense of the scale of the coming events. And in the case of Pinatubo, it was a very interesting sort of evolution of events, because They looked at the seismic activity, and the seismic activity showed this progressive increase with time over a period of months. They looked at the geodesy, the deformation changes in the volcano. They could see magma that was coming up into the volcano. And they were tracking the gas discharge. And they saw that the gas discharge rate was increasing over this period of time. But, and it's a little bit counterintuitive, because what they found was suddenly the gas discharge rate dropped. It almost turned off.
The calm before the storm.
Well, they looked at that data. The seismic activity continued to increase. The deformation continued to increase. And there were two interpretations of the gas discharge rate. One was, well, it's going to go back to sleep. The other was that our pressure relief valve has become plugged. And clearly, with continued seismicity, continued deformation, it was like, okay.
That makes it worse.
That makes it worse. We need to evacuate. And it was that type of analysis that led them to say, okay, within the next 48 to 72 hours, it is highly likely that there will be a catastrophic eruption.
And they were right.
And they were correct.
It was right in that zone, in that time frame.
Yes, it fell within that time frame.
That's terrific. Yeah. Wow. And this was good enough for a movie, actually. Did they make a movie? I don't know.
They made a documentary, but
okay.
I don't think they made a movie of it.
So, but at the end of the day, it's between 24 and 48. And it's, it's either bad or very bad, somewhere in the zone. I mean, how much of we talked about this before, how much of a science is this? And does your nose count in terms of experience, of having watched this over a period of time?
Well, let me state it this way, that a significant part of your mindset in trying to forecast these events should include humility.
Mother Nature.
Mother Nature will do what Mother Nature wants to do.
Okay.
And it certainly is far from a perfect science. There's still very much that we would like to know that we don't. And really that's why we continue to study these volcanoes. With every eruption, we learn tremendously. And one of the things that I tell our students and trainees is that these things have been going on for geologic time. We will continue to learn from them for geologic time into the future. So we can make our best estimates, and I will tell you the same thing I tell my students. I refuse to use the word predict and volcanic eruption in the same sentence. I think a sort of a better representation is we forecast. We make a forecast.
Like the weather.
There is always a probability that we will be wrong. Mm-hmm. So, we do the best we can, but still, there's a great deal we have to learn yet.
Well, speaking of learning, it strikes me that since Pinatubo and since, 10, 20 years ago, you've seen it. You've seen the dynamic in this science.
Yes.
And I wonder how you feel, what you think about the speed at which the science is moving, and how much more accurate are these forecasts now than before?
Oh, there's been since I started in the field back in the 1970s, we've made tremendous progress. When I started, one of our challenges was, how do we get a measure of the gas compositions coming out of the volcano? How do we estimate a mass emission rate of these gases from the volcano? There, and literally, the volcanologists sort of the day would make estimates. They would throw a feather into the fumarole discharge and estimate its rate of rise and say, okay, we can estimate what the volume of gas is. Our methods at the time were extremely crude.
This is in our lifetime.
Yes,
we were doing
in our
this.
lifetime. And now we have instrumentation, some of it actually being perfected at the University of Hawaii, that will give us very good data on masses of these gases coming out, of individual gases. And I say we've got new technology that's been developed that will give us actually a broader spectrum of the gases. And this is entirely remote. We can stand off from the emission point, you know, aim our laser or our infrared detector at the gas plume and get, if not a complete analysis of the gases, we can get really 95% of the gas composition from these very sophisticated advanced instruments.
And then you can map that as to where you got it from and put it in a model, which the model is probably one of those dynamic things that gives you a better advantage all the time.
Exactly. Exactly.
And the model is something that evolves. I mean, it's just not like you invented it yesterday, but you did improve it yesterday.
Yes, yes. It's a process of continual improvement, and as we apply it to different volcanoes, we can then increase the sophistication of the model, adapt those models for the particular type of volcano that we're dealing with.
So you take your computer, about that big, it's got the model in it, okay, and there's something going to happen in, I don't know, say Italy. I think of Italy and volcanic eruption, okay, because there have been reports from Italian authorities, and they don't know exactly how to cope with this. So you and your troop, you go over to Italy, and you fill in the blanks. The Puca's in the model now, filling in a lot of fields, and then you can make the same kind of prediction, A or nay, or how bad and how long, that science could have made, that did make in the Pinatubo case.
That really is our objective, is to, and we collaborate, and actually, I would say that your choice of Italy as the country that needs help is not the best choice, because they have very good volcanologists there. We collaborate within our institute and school. We have many collaborations with the Italian scientists. And again, together we, along with British and Icelandic, there are many of us in the field working on these problems, and together advancing incrementally as we collect more data for new eruptions, new volcanoes, new geologic environments. Because in a sense, each volcano has unique aspects, and we actually can, it's not just a matter of monitoring the active volcanoes, it's also doing very intensive analysis of the chemistry. We've developed new tools that can give us the gas compositions. We can compute the gas compositions that were present in the magma at 30 and 40 kilometers down. No one would have dreamed of doing that when I got started. How do you go that far down? Well, we take minerals, individual minerals that contain the gases. They were in equilibrium with the gases at 30 and 40 kilometers below the surface. We just didn't have any way until recently to actually do the analysis of the gases contained within those mineral separates.
So you don't have to go down that far.
You don't have to go that deep.
You're looking at the surface,
we can't. Right. We're looking at the deposits at the surface, and then by analyzing those deposits at the surface, we can essentially track those minerals during their pathway, during their history, as they interacted with the magma coming up to the surface before and during the eruption.
Again, because you can make the assumption that things are pretty much the same, and what happened before will happen again.
Exactly.
So let's take a short break. When we come back, Don, I'd like to get into the point you made about, Italy has its own, scientific organizations. But I'd like to ask you when we come back, so where are the active volcanoes, and where are the active scientists? and how do you put them together? That's Don Thomas. He's with UH. He's a volcanologist. He's based in SOES, the School of Ocean, Earth Science and Technology, and within that, the Institute for Geophysics and Planetology. Okay, we're talking about sustainable Hawaii, and we're talking about Pahoa. We're going to get there. A hot time in the old town of Pahoa tonight. We'll be right back.
Aloha, my name is Carlos Juarez, and I host Global Connections here on the ThinkTech broadcast series. We broadcast live every Thursday from 2 o'clock, and also on Olelo 54. Please make sure to tune in and join us. We'll see you there.
This is Alice Lee Hagan, host of ThinkTech Hawaii Business Education Spotlight. My show here at ThinkTech Hawaii is every Thursday from 3 to 4 in the afternoon. I bring in interesting guests from Hawaii, the mainland, and hopefully international guests in the future. Do join us on Thursday from 3 to 4 p.m. ThinkTech Hawaii Business Education Spotlight. Aloha.
Okay, we're back, we're live, we're here. I'm Jay Fidell, that's Don Thomas, he's a volcanologist. We're talking about a hot time in the old town of Pahoa tonight, here on Sustainable Hawaii, part of the ThinkTech series. So as we left it, we're gonna explore a little bit about the the globality. I like that word. The globality of volcanoes and the globality of the scientific establishment that studies them and makes forecasts and so forth. Can you address that? I mean, we know Iceland, we know Italy, we know Pinatubo, we know Hawaii. But what else?
Well, I mean, we have, of course, the classic Ring of Fire. Japan has a very active volcanology program in many of their universities and have done and continue to do great work. Of course, if you get up into the Kamchatka Peninsula, there are many Russian scientists who have studied the active volcanoes there. And we are gradually developing a cadre of scientists in Central and South America. We have all of the volcanic activity extending from Mexico, Nicaragua, Guatemala, Panama, and into Colombia and Chile. We had a major eruption in Chile just a few years ago. And they're gradually developing their capabilities to analyze their volcanoes and manage their volcano hazards there. Of course, in Africa, there are a number of volcanoes. Many of the volcanoes are in former French colonies, and so there's a very active community of French volcanologists as well.
So, wow, it sounds like it's everywhere.
Absolutely.
So the Earth is riddled with volcanoes.
Absolutely.
Why is that? I mean, where do you find a volcano? What set of circumstances have to exist in in the way the Earth is built to find a volcano at a particular place?
Well, there are several fairly special circumstances that produce volcanoes of different types. Hawaii is sort of typical of one type of volcano. We have what we refer to as a mantle plume. We have active circulation deep within the mantle. Our currently accepted model is that magma is being generated at a depth of about 100 kilometers below the Big Island. There's a rising plume of material coming up through the mantle that produces that magma. And it produces a magma of a particular type. Iceland is a very similar type of situation. So where we have this mantle plume activity is where you see active volcanoes. Yellowstone, the volcano responsible for Yellowstone is one of these mantle plume volcanoes. It just happens to reside beneath the North American continent. But then another fundamentally different type of volcano is where you have tectonic plates colliding. So we have the Pacific plate being subducted in the Aleutian Trench. And so all of the islands all the volcanoes in the Aleutian Islands are derived from that subduction process. Similarly with the Japanese volcanoes, the Philippine and the Indonesian volcanoes, and the Central and South American volcanoes are associated with subduction processes. And so those are the primary types of processes to generate this active volcanism.
So it's like a flaw in the surface of the Earth. It's like something isn't connected quite the way you'd want.
Well, it's a little more complicated than that. The subduction process, actually, what happens is that the tectonic plate, as it's being subducted, it sort of has resided at the surface. It's absorbed lots and lots of water and lots of what we refer to as volatiles. As that's shoved down deep into the Earth, those materials are heated up, and a portion of that plate is melted. And that material wants to come back to the surface. And so those are the subduction type volcanoes. And their chemistry is fundamentally different from the mantle plume volcanoes.
So it's a question of heat then?
Yes, yes.
However the heat gets created,
right.
Heat will find a way up.
Right.
And when it finds a way up, it's actually a plume, and the plume is going to lead to an eruption or some kind of seismic...
You will have volcanic emissions,
yeah.
Whether they are solid, liquid, or gaseous.
Okay, so when you say there's a plume under the Big Island, probably right around Pahoa.
Larger than that.
Larger than that.
Okay.
It means that somewhere down deep, say 100,000 kilometers.
No, 100, about 60 to 100 kilometers.
100
magma
kilometers.
is being generated.
And so there's something going on down there, and the heat is transmitted through the rock, through the whatever it is down there, and the heat in one layer is going to heat the next layer, and it transmits the heat all the way up. What happens?
No, what happens is that we've got this material rising from very deep.
It's actual material rising.
There is material
it's not just
rising.
Heat
It's
rising.
not just heat. No, it is material rising, and as it rises up near the base of the crust, it begins to melt. And again, fairly complicated process, but that partial, what we call partial melt, that then becomes more mobile and more buoyant and can rise up to the base of the island, and ultimately what it's able to do is work its way through the island up to the surface, or through the crust up into the island, and then to erupt.
Okay, is this degree of what's happening on the Big Island, you know, small or large, on sort of on a world continuum of that? Is this a big deal, looking at it as a global phenomenon, or a little deal?
Well, within the global context, it is actually fairly small, but it's been going on, we know, for at least 80 million years.
Just the way it is now.
Just the way it is now.
Repeated.
It basically, Oahu, about 4 to 5 million years ago, was where the Big Island is now, and that's what formed Oahu. It also formed Meiji Seamount, which is about 75 million years old, that's just about to be subducted into the Aleutian Trench. So the entire Hawaiian island chain was at one time where the Big Island is now. And that process, again, as I described the lava flows, is relentless. It continues and has continued for 80 million years, and perhaps much longer than that.
So we are changing.
Oh yeah.
I mean, over 80 million years we are changing. Yes. So is there a model? Do you have an idea, even a personal idea, about what the state is going to look like in another 80 million years?
Well, in another 80 million years, the Big Island, Oahu will already have been subducted. Oahu will be gone without a trace.
Forget about your fee simple land. Yeah.
Right, exactly. You're going to have to drill very deep to get to your fee simple land in 80 million years. But the Big Island will be up where Meiji Seamount is, and will be approaching subduction. There won't be much left of it. It will probably be a very small vestige of what it is now. And again, this process, the Earth is billions of years old, and so this is really only a very small segment of the life of the planet itself. And this process, we have every reason to believe, will continue for another 80 million years.
Yeah, well, it's really interesting. It's part of Hawaiiana for sure. It's part of the land. It's part of sustainable Hawaii. It's part of our whole environment. It really is.
Exactly.
And you know, you wonder. It's like almost like sharks. You know, nobody hates sharks. Well, some people must hate them, but nobody hates sharks because they're part of our environment. They're almost a piece of trophy that we're proud of having, proud of dealing with, and all that. So the volcano. It makes us interesting and unusual, no?
Yes, absolutely. It does, and without the volcanic activity, the islands wouldn't be here. And it goes back
where thanks are due.
It goes back to the traditional view, the Hawaiian view of Pele. Pele is both a creator and a destroyer. That volcanic activity is what gave us the islands.
Yeah.
But it also can destroy man-made plans, and
this could make you a religious person. Mother Nature, you know. But it's okay. Now it comes up, and you can see it come up because there's this black and red hot stuff. You can feel the heat from, you know, hundreds of feet away, and smoke and smell, a sulfur smell, I guess.
Right. Yes. Sulfur dioxide.
And what temperature is it coming up at?
It's coming up at about 1,100 degrees Celsius.
That's way high.
Yeah, that's about 2,000 degrees Fahrenheit.
Okay, so nobody can exist in that. Nobody can put his toe in that.
No.
Even the strongest hiking boot won't last but a second.
No. It's a very temporary thing. Those temperatures, there's very little that would survive exposure to those temperatures for any significant period of time.
Okay, and when it runs down the hill, how fast does it run?
I'm afraid I'll have to give you
It depends.
right,
answer.
exactly. It depends on how steep the hill is.
Okay.
Some of these lava flows can advance very, very rapidly. This is one of our concerns on the Big Island, where with this Kilauea flow, it's taken several months for the lava flow to get down to Pahoa. If we have an eruption, or when we have an eruption on Mauna Loa's southwest rift zone, it can go from the eruptive vent to the ocean in 2 hours, 4 hours, 6 hours. So it can move very, very rapidly when we're dealing with a very steep slope.
But never so rapidly that you can't see it coming at you. Never so rapidly that if you're awake and alive and watching and smelling, you'll get out of the way, right?
You should be able to get out of the way. But the best thing is not to be downhill of it. I mean, the guys that do work with the lava flows, you get out into some of this very, very rough country, and you would be struggling to get out of the way of some of these fast-moving flows. But in general, the flows don't really pose a life safety type risk. The greatest risk is to infrastructure, to whatever we have constructed on the land.
So if indeed, you know, there's a certain forecastability about it in terms of location and the track of it as it goes down, and we know what it is and the temperature it's likely to have. How come people buy residential property directly in the line of fire?
Well, unfortunately, the human time horizon is much, much shorter than our geologic time horizon. And the last time much of this area was covered by lava flows was 500 to 1,000 years ago. And one of the things that our program at Hilo does is to do outreach to educate the public. And what we could say is, I can guarantee you that this land will be covered by a lava flow. I am as certain of that as I can be of anything. What I can't tell you is when. It may be next year, it may be 50 years from now, it may be 500 years from now. But I can say with certainty it will be covered. It's very difficult for people to integrate that into kind of an everyday risk.
Or a title company.
Or a title company.
They don't know what to do with that. I mean, I doubt, I've never seen it, but who knows, where the title company says, if you hadn't noticed, this is in a lava flow area, and your land, you know, in a year or 2 or 10 or 20 could be buried.
Exactly.
And therefore you shouldn't buy it, or therefore you can't get title insurance on it, whatever.
Right, right. It's what sort of the inevitable is now occurring with Pahoa. And we've known, all of us in the field have recognized that Kilauea resurfaces itself.
Like a roadway.
That's what we call it, like a roadway. It resurfaces itself on a regular basis. And we cannot, we're a long ways from being able to say what Kilauea will do 50 or 100 years from now. We can't make those kinds of forecasts. We can say over the next 200,000 years, though, it's likely that this region of the volcano will be covered multiple times. But again, that's not the kind of information that a member of the general public can work with.
But there is information that you could provide to say, hey, it's coming down the mountain. You can see it over there, and it's going to come so fast, or maybe it's going to come next week. But we know this because of our models, and we're here to tell you it's time to evacuate. And I suppose you have done that in Pahoa.
Well, yes, Daryl Oliveira has, and I mean, we have told individuals, we have done public outreach programs to tell people, look, you know, this area is at risk from a volcano. But once the flow is sort of active, then sort of the responsibility for managing that then goes to the folks like Daryl Oliveira, who is the Civil Defense Administrator, and they really are managing that to the extent, of course, that they can. They're trying to manage that event to minimize the adverse impacts on the community. And many people envision the lava flow as simply being, well, it's going to cover your house. A lava flow can cause tremendous disruption without touching a single house. All it has to do is deprive you of your infrastructure, deprive you of your access to the community. This is one of the biggest impacts of these flows right now is Highway 130. If Highway 130 and the other access routes in and out of Puna are cut, tremendous economic and social disruption is going to follow.
How long does it take for this 1100 centigrade material to cool to room temperature?
Well, once it's in place, it can cool off in a matter of days. The problem is, though, that these flows, as we're seeing right now, is they don't move tremendously fast in relatively flat topography, but they will form layers of 10, 15, 20 feet thick that will take days, weeks, or months to cool off, and they will gradually sort of expand outward to cover progressively more ground. And if that sort of expanding blob is across your road, there's nothing you can do about it.
When it cools, what's the hardness of it? You know, can you like chip it away? Can you take a bulldozer and push it away?
Oh yeah, absolutely. You can break it up. And in fact, I mean, they're doing some of that right now, where the flows that came down on the Kalapana side of Kilauea covered Chain of Craters Road. They've got multiple D9 dozers in there trying to break that down and trying to make an access route along the old Chain of Craters right-of-way. That kind of is our last-ditch safe pathway that is not currently threatened by a lava flow. And in order to preserve that access, the county and the state are working very hard to make that that pathway into a usable roadway.
Can you use the lava material as roadway material? It looks like, you know, asphalt. Is it? Can it be?
Oh, it can be broken up. It really would not, say, be tremendously useful as aggregate, simply because it still, in much of it, it's too friable. It's too easily broken down. They like something a little bit more durable than the surface of the lava flow, anyway, as aggregate material. But you know, again, this is the problem, and our fear is that the eruption has been going for 30 years now, more than 30 years. It could continue for another 30 years. We have no way to forecast sort of when the flows will stop coming down on the Pahoa side. And what I tell people is that, you know, the volcano is not necessarily dangerous to your life, but it is relentless. And as long as these flows come down, they will disrupt access, disrupt utilities, disrupt essentially the entire lifestyle in Lower Puna that needs to get back and forth to Hilo.
So one last question, Don, and that is, you know, it seems to me, you can agree or disagree, that Hawaii as a center. We have the resource to study, and we have a body of scientists, and we have a body of knowledge, and we become a valuable asset in the scientific world to teach other people.
Yes.
And you mentioned before we started the show that you had a training program that brought in people from 24 countries.
Yes.
To teach them this, and they can take it back and use it. So this is different. This is something that did not exist in 1972.
No.
Can you tell us about the program?
Well, the program was actually initiated back in 1990, and it really was it was initiated in response to a very terrible eruption that occurred in Colombia during the mid-1980s. A relatively small eruption. It was not, the country of Colombia was not able to manage the hazard. Things didn't go well. A relatively small eruption generated a debris flow that killed 23,000 people.
Whoa.
One fell swoop, 23,000 people, and every single one of those people could have walked to safety if they had known what to do if they had known how to respond to that event.
So this program you're working on is directed at that kind of scenario.
Yes, exactly. What we're trying to do is provide training, and our primary focus is developing nations. And so all of the developing nations, we even have had trainees coming in from the Goma Volcano Observatory in the Democratic Republic of the Congo. We bring in trainees from all over the world and we provide them with training that is on the one hand consistent with what they can do in their country, what the types of monitoring that can be done with the technological infrastructure that they have. In some countries, they have very limited technology infrastructure, and it's of no use to them to give them a mass spectrometer. They cannot maintain.
So you have different levels
so
to deal with.
We try to train over a spectrum of levels that each of the trainees can take back a body of knowledge that they can apply in their particular circumstances with the technology that they have access to. And at the same time, tell them about more advanced technologies that when an opportunity arises, then they know how to advance the state of the art for their country.
Well, this is part of SOWEST.
It is.
You have a
SOWEST is
subsidiary organization.
It's the Center for Study of Active Volcanoes.
And that's the organization that trains these
that
people
does the
coming.
training. Yes, yes.
Well,
And
I think that's really
it's a partnership between SOWEST and the University of Hawaii at Hilo, and they are very much partners in that effort.
That's great. You are a hero for being involved in that, Don. Don Thomas, a volcanologist at UH in SOWEST here and in Hilo, and studying volcanoes for more than 40 years. And here on Sustainable Hawaii, we've been talking about a hot time in the old town of Pahoa. There's more to come. We'll talk about seismic activity in connection with geothermal, and I hope you'll come back soon.
Sure, I'd love to.
Thank you, Don Thomas.